we are ready to start now. And our speaker today is Alexey Basalaev from Higher School of Economics, Moscow.
And
so, please, you are welcome. And Skolkovo.
Yeah. Yeah, thanks a lot for the introduction and also for the invitation to speak. So I'm going to speak about the integrable systems or integrable hierarchies, but from the point of view of such objects as the Dubrovin-Frobenius manifolds. So I'm going to present some new construction, but actually there are already many constructions that associate integrable hierarchies to the Dubrovin-Frobenius manifold. Those are given by Dubrovin and Zhang since 2001, and well, that hierarchy is associated to any Dubrovin-Frobenius manifold. Well, that's well, it is defined rather easily. So as you see on the screen, theta is some data that is computed from the Dubrovin-Frobenius manifold, and v is some unknown function. So it's easy to write down the hierarchy dispersionless, but the problem is that after that you have to deform it to get a hierarchy in all genera. So there are other constructions due to Alexander Buryak, the so-called DR hierarchy. Well, it is associated not actually to a Dubrovin-Frobenius manifold, but to a Koch-F-T, to the cohomological field theory. And the difference is that the Dubrovin-Frobenius manifold can be thought of as a genus zero data of a Koch-F-T. So from this point of view, Koch-F-T always has much more information than just the Dubrovin-Frobenius manifold. And there are many other constructions, like, for example, due to Frenkel, Giventhal, and Milanov, but not for any Dubrovin-Frobenius manifold and not for any Koch-F-T, but well, useful for the particular cases, like, for example, ADE cases. Well, there are also more specific constructions due to Mokhov or some others. So I'm going to present a new construction that is not that general, that cannot be associated to any Dubrovin-Frobenius manifold or to any Koch-F-T. Well, it will not be that involved, like, for example, Frenkel, Giventhal, Milanov construction, but I think that it will be, first of all, way easier to touch. So, well, what is known about the relation between the different integrable hierarchies that we had on the previous slides? So DZ, that is a short name for Dubrovin-Zhang hierarchy, for AN type Dubrovin-Frobenius manifolds, it is equivalent to the reduction of KP hierarchy. And essential question that is always here is what is the relation between the DR hierarchy of Buryak and Dubrovin-Zhang hierarchy. So in this case, in the particular case of one particular series of Dubrovin-Frobenius manifolds, well, it is known that they coincide differentialless, but it's not clear how they are related in full generality. Well, for the more general cases, like, for example, Dn Dubrovin-Frobenius manifolds, it's only known that Dr is equivalent to Dz dispersionless. And, well, after the well, very important paper of Liu Wu Zhang, touching all the possible ways to construct Dn hierarchy, well, it is known that Dubrovin-Zhang hierarchy is also a reduction of a well-known, well-studied hierarchy. It's not KP hierarchy like it was for AN first, but it is a reduction of a two-component BKP hierarchy. So, and one very interesting result concerning this DN type Dubrovin-Frobenius manifold hierarchies is that these hierarchies have two distinguished sets of types. So namely, if you define this hierarchy as a set of evolutionary equations, then you have to special times, and they evolve in their own manners. So in particular, one of these sets corresponds to the first component of BKP hierarchy, and the other set corresponds to the other component of BKP hierarchy. And well, these components should be reduced. So this is 2n-2 reduction, and they are reduced differently. And there is an essential question. So how does it come that in this particular case, we have not just one set of times, like it is, for example, for KP hierarchy. It's infinite set of times, but one set of times, but two sets of times. So, and in my talk today, I'm going to do three different things. So that was introduction. I believe that not every word there was clear for everyone. I'm going to explain all I need in what follows. So, and I'm going only to speak about the commuting systems of partial differential equations that can be written in the following particular form. So it will be, in my case, the following equality, the second order derivatives of f being expressed via the also second order derivatives of f, but one of them being always with respect to the first time. So d alpha is d by dt alpha. So the r's on the right hand side should be some fixed set of constants. F is an unknown function, and this set of constants is exactly what defines the system of PDEs. Well, there is an essential question of, why do and should such system of PDEs commute? So this will be some condition on the set of constants R, and well, we will speak about that. Why is this good? Why is this form good? Well, because it explains the dependence of f on the higher order derivatives with respect to the some initial condition data, and this is the derivative of f with respect to the first time and well all the other times. So some sort of initial condition. And well, I'm going to construct such systems of PDEs from the Dubrovin-Frobenius manifolds. Well, I'm going to present the particular way how to do such things. And also with that, I'm going to explain indeed why should DN-type Dubrovin-Frobenius manifolds have two series of flows, two series of variables, as it was t and t hat on the previous slide. So I have a good explanation from the point of view of the Dubrovin-Frobenius manifolds. Well, and well, maybe we will go beyond the theory of the Dubrovin-Frobenius manifolds. Well, that is not covered even by all the hierarchies I've explained earlier. So why this particular form of PDEs? Consider the special as KP. It can be written in the following form. Let's introduce the following numbers. We take ij and m, positive natural numbers, and we denote by this Pij all the possible partitions of I and partitions of j that are not independent, but subject to some additional conditions that sum of ak plus jk is gamma k plus 1. Then set R, I use here the superscript a in order to indicate that I take the particular set of constants R. I will use this particular set later. So if you take it to be in the following form, then the dispersionless KP hierarchy on the logarithm of a tau function can be exactly written in the way, well, I have presented in the previous slides. So the dispersionless KP hierarchy fits in the setting we're going to use. So this is just dispersionless. I should probably explain why, but it will be clear from the next slides. How? The point is that there are many ways how to write down KP hierarchy, and one of them is in a Phi form. It is not that well known, but it can be easily derived from the integral form of KP hierarchy. So recall that in the integral form, we have, the PDEs of the hierarchy are written on the tau function. Here, my f small is a logarithm of a tau function. And in that tau function, we should consider the residue of some exponent multiplied by tau, dependent on t, and dependent on multiplied by t and tau dependent on t prime. So I have two sets of variables t. And this is a simple trick that allows one to write down the same equations, but not with two sets of times, but with two sets of additional observable variable. This is in my case Z1 and Z2. So the following equation we have on the right-hand side, it should be read off as the equation of the formal power series on Z1 and Z2. And well, this is exactly the KP hierarchy in the Phi form. And recall, if you take H bar to be equal to 0, then you get exactly that delta Z is equal to dz. And taking the logarithm on both sides, you get exactly what we had on the previous slide. And important theorem of Nathanson and Zabrodin says how to get the full hierarchy as it is written in a Phi form, y is this exponent, y is the dispersionless limit. And it is very simple. You should take the same setting. So you should take again this equation d alpha d beta f is equal to this big sum. But now on both sides, you replace the differential operators d alpha that are d by dt alpha by the more complicated operators that depend also on the variable h. So why is this important? That's important because that's a way how to get the full hierarchy from the dispersionless limit. And that's an essential point in all the hierarchies that are built from the Dubrovin-Frobenius manifolds. Because the Dubrovin-Frobenius manifold should be thought of as a genus 0 data, and therefore corresponding only to the dispersionless limit. So if you want to construct a full hierarchy, you should take a dispersionless limit and give a clever way how to extract all the other flows or the full hierarchy, not just dispersionless limit, from its dispersionless limit. So from the genus 0 data. In this case, it is done basically by substituting the alpha deformed by h instead of d alpha. So who are the Dubrovin-Frobenius manifolds? Well, the theory of the Dubrovin-Frobenius manifolds is rather big. And I'm not going to introduce it fully, but actually every Dubrovin-Frobenius manifold is locally described by its potential. It's one big function that depends on n variables and should be the dimension of a Dubrovin-Frobenius manifold. And this function should be of a very specific form. First of all, the role of V1 variable should be distinguished in the following way that it enters the potential f only in the cubic terms as written. And these cubic terms should be, well, not something. So these cubic terms should be organized so that they give a matrix eta alpha beta. And this matrix eta alpha beta should be non-degenerate. So this matrix should be constant. Well, it doesn't depend on V, and also its determinant is non-zero. And the remaining part, well, all the remaining summands of f, they are given by some function h, and it does not depend on V1 anymore. Well, that's a first well, first important condition on this potential F. And the second, very important, and that was actually the start of to study the Dubrovin-Frobenius manifolds, is that they should satisfy WDVV equation. This WDVV equation, well, it is written here. It is a huge equation, so its origin is in the study of genus 0 stable curves. So it came from the modular space from Koch of T's in genus 0. But in here, we're going to look at it really differently. Because if you know that your function f satisfies WDV equation, then you can just formally introduce the following product. D by dv alpha multiplied by dv by d beta with the help of the structure constants that are introduced via the third derivatives of f. So here I have eta with the raised indices, and these are the components of the inverse matrix. So it can be inverted because it was non-degenerate. So now all this big WDV equation is nothing but an associativity equation of this product. So this product is commutative just because the partial derivative associativity doesn't follow from anything, so it's an additional requirement, and it is equivalent to WDV equation. Well, the sources of the Dubrovin-Frobenius manifolds, well, there are many. First of all, any genus 0 part of a Koch of T is it defines the Dubrovin-Frobenius manifold because it defines a solution of Koch of T, a solution of WDV equation, and also the role of a unit is very special. Well, completely different source of the Dubrovin-Frobenius manifolds come from the formation space of isolated singularities, and also different source of the Dubrovin-Frobenius manifolds is invariant theory of reflection groups. In particular, examples of such invariant series are given by the simple reducible Coxeter groups. These are AN, DN, and E types, and also distinguished corresponding to the root systems with the roots of different lengths. These are B, F, H, and I. So in all these cases, the orbit spaces of the complexified action for Coxeter group has the Dubrovin-Frobenius manifold structure. The manifold itself is Cn, on which the variables V live, and the potential F is just polynomial. So examples of these potentials are, for example, the following. In my talk, I will be in particular interested in the examples of Coxeter groups of type A and D. Well, that has to be proved, but if you consider the singularities of types A and D, you also get the same Dubrovin-Frobenius manifold structures. So they will be isomorphic. One can construct an isomorphism. So it's it's Saito theory. So here are examples of these potentials, and the point is that if you can make sense of, for example, the product that was defined by the Dubrovin-Frobenius manifold, if you can make sense of this product in the invariance theory of Coxeter group in the unfolding of a singularity, it's really a big question: what do these functions f give? So after you write them as these potentials, so some enumerative meaning or whatever of this function is already, well, not clear. So, well, the function itself is very useful because you can write down the product in a very simple way. Well, but after that, that's the only useful thing you can say about these functions. Well, but we're going to use them today in order to construct exactly these integrable systems. So our approach is the following. one considers not just one Dubrovin-Frobenius manifold, like it is done, for example, in Dubrovin-Zhang theory, like it is done in the DR hierarchy, where one takes one cohort. No, we take infinite series of Dubrovin-Frobenius manifolds. Indeed, infinite. So it's important that we take infinite series. We consider new variables. I call it V delta hat. And these new variables are defined by the following formula. Well, those are dual. Dual in the sense that V gamma, d by dv gamma, is paired with d by dv gamma bar. And then define the following functions. Define R alpha beta with the additional set of gamma 1, gamma m as the higher order derivatives of these fn's. Obviously, on the right-hand side, we have a special dependence. Well, on the left-hand side in R, we have alpha and beta playing a special role concerning, for example, gamma 1, gamma m. And this is reflected on the right-hand side in the following way. We take the derivatives with respect to the V alpha and V beta, having alpha and beta indices on the left-hand side. But if gamma 1 is an index on the left-hand side, on the right-hand side, we take the derivative with respect to the gamma 1 bar. So obviously, here is a small thing. So the capital N does not pop up on the left-hand side. Well, that's the approach, and it provides some some construction. It only works if this set of R's are well defined. Namely, that Fn's satisfy some stabilization condition. Namely, that you have Fn with some n capital dependent on alpha and beta only on alpha beta, so that all the other dimensions n's higher than this first one, lower bound for n alpha beta, providing the same numbers R alpha beta gamma 1 gamma m. And then we introduce the system of PDEs, well, exactly as it was described earlier. And if this works, if there is a way to construct such R's, namely if the system of Fn's satisfy these stabilization conditions, then this system is automatically consistent. So we will prove it later, but actually this is just WDVV equation, something really super essential that is in every Dubrovin-Frobenius manifold. So examples of such stabilization are rather easy. So take, for example, f of A4 and A5. So those are given by these two potentials. And in these two potentials, consider the second order derivatives with respect to V2 and V3. We get different expressions. In the first case, this is V1 minus V3 V4. And the second case, this is V2 minus V4 V5. But recall that on the left-hand side, we had alpha and beta the same as on the right-hand side when computing the constants R. But gammas are taken to be gamma on the left-hand side and gamma bar on the right-hand side. So I have to make a substitution. Well, and the point is that V1 for A4 is V4 bar, and V2 for A5 is V4 bar. So in this way, I get the same expression for both A4 and A5. So the general statement is the following. So we did it together with Piotr Dunin-Barkowski and Sergei Natanzon. And well, we have observed that if one takes the Dubrovin-Frobenius manifolds of A-type, then the potentials satisfy the following stabilization condition. So you take the partial derivatives of two different potentials with respect to the same V alpha and V beta. But after that, apply the change of the variables. This is actually the same change of the variables that makes V gamma bar from V gamma. So I didn't, well, we didn't check it here, but actually the eta alpha beta is introduced so that this S gamma in both cases is actually V gamma bar. Then you get the following equality, and this is equality of polynomials. So if you get equality of polynomials, then it is equivalent to the equality of the coefficients of the monomials. So the coefficients of these monomials will exactly be these constants are alpha beta gamma 1 gamma m that will give me system of commuting PDEs. For the D case, the situation is a little bit different. Recall that for the D case, we had two special systems of flows. One system of flows given by one set of variables, and the other system of flows given by the other set of variables. So, and already here we see that there is very special stabilization. Namely, the last line is very similar to what we have on for A type. It's indeed just partial derivatives with respect to alpha beta, but in here the condition is that the sum of alpha beta is less than n1. That means it is also less than n2, and that means that none of alpha or beta can be equal to n1, so the last special variable of dn. And the special dependence on this last variable is given by the first D-type line. And here, look, we have the derivative with respect to n1 dv beta and dv n2 dv beta. So this is some special stabilization condition for n1 and n2 in D-type and A-type. And right here, this is only a statement about the Dubrovin-Frobenius manifolds, maybe also about the singularities and the flat structures of Coxeter. So what we get from here? We get that if one defines takes this FAN as an infinite series of the Dubrovin-Frobenius manifolds, namely going exactly this approach, then we have proved that this FAN satisfy the stabilization conditions. So these R's alpha beta are well defined. Then one can introduce the system of PDEs, reading off the coefficients of FAN. Well, and example of this flows that we get from here is the following. So you take the second order derivative of f a4 with respect to dv2, dv3 in the s variables in which this expression stabilizes, we get s4 minus s1, s2. And in order to get a system of PDEs, we should now consider the derivative of f now in the variables t2 and t3. And it should be equal, well, you should just do the following. You take this expression s4 minus s1, s2, and in all the places of s4, you write d1, d4f, and instead of s1, you write d1, d1f, instead of s2, you write d1, d2f. So very simple. And the system of PDEs you get in this way is exactly the special SKP hierarchy. So this is something that has to be proved. This is some combinatorics of A-type Dubrovin-Frobenius manifolds. So due to the results of Natanzon and Zabrodin, we know that the full A-type hierarchy is obtained by a simple substitution. Decay substituted by decay H. So this decay H should be a very particular expressions. These are the same we had previously. And well, the system of PDEs that one gets from the D-type Dubrovin-Frobenius manifolds, it coincides with a one-component reduction of a two-component BKP hierarchy. So this is a small difference. Recall that for one AN Dubrovin-Frobenius manifold, Dubrovin-Zhang theory gives n minus 1's reduction of KP. So we consider not just one Dubrovin-Frobenius manifold, but an infinite series. And in this way, we don't get any reduction. So we get a full KP hierarchy. For D-type, we still have some reduction, but it's just one component reduction, not two component reduction as it was for one instance of Dn. So why does D-type system has two special flows? The point is that, well, it originates from the fact that these FDs have different stabilization properties. And these different stabilization properties give different constants R. So in particular, these different constants, they come in two types. I use here the superscript D1 and D2. And look, the first two are, the first one, D1, has two variables alpha beta, and D2 has just one variable alpha before the semicolon. That's because in there one fixes the partial derivative with respect to the last variable. So we know that these numbers do not depend on n. And then the flows one gets are the following. So this additional variable here is just T0. T1 and T2 are all the old variables as we had before. They build up their special system, and well, it is independent on the variable T0. So all the dependence on the variable T0 is given by the second line, and this second line is defined by the constants RD2. So why is it so? So the reason for that is, yeah, well, here are some examples. Yeah, here are some examples. So, well, these are, on the first lines, these are the sets corresponding to the first system of flows and the second of the second system of flows. So, why so? So, why does it happen that we have in Dn the two distinguished systems of flows? This is because of the following. That actually, indeed, previously we were writing down these systems of PDEs via the constants R. But actually, one can do it without really employing these constants R. Recall that these functions f were the polynomials. And actually, everything that these constants R were doing are taking the second order derivatives of f with respect to its own variables, v alpha and v beta. So the function f depends on the variables t, and well, you take the derivatives of f with respect to the other variables, v alpha and v beta, but after that you substitute every variable with d1 df, well, f being a known function, but well, also with some use of the pairing. And what is so special about the D-type is the following. Recall that the Dubrovin-Frobenius manifold has a product. Well, it's a very special product defined by its potential. And the special property of D-type Dubrovin-Frobenius manifold is that its last variable is distinguished. If you consider the product of any two vectors dv alpha, dv beta, with alpha and beta not equal to n, then expressing this product, you get a combination, well, linear combination in some functions that does not depend on the variable Vn. So the coefficients do not depend on Vn, and also none of the vectors d by dVn presence. So in the language of the Dubrovin-Frobenius manifolds, you can say that Vn equal to 0 is a submanifold. Well, it's not just a submanifold in the usual sense, in the sense of the complex manifolds, but the point is that also the product structure respects this, this restriction to Vn being equal to 0. And that's actually the reason why d1, d by n minus 1 build up their own flows. Namely, if you look again at the first line on this slide, you should write down d alpha d beta f. And in order to say what should be this flow d alpha d beta f, you consider the second order derivative of f capital with respect to v alpha v beta. Well, and the second, the potential of the Dubrovin-Frobenius manifold, it is responsible for the product of the Dubrovin-Frobenius manifold. Then the point that the product of v alpha and v beta does not depend on d by dvn exactly corresponds to the fact that in the flow d alpha d beta f, you don't see any variable vn popping up. And if vn does not pop up, then the condition on the substitution says that also the vn d by d eta n does not pop up too. So why do these flows commute? Well, we have to check a very basic thing. We have to check that if you consider the third order derivatives of f, then it does not depend, the expression you get does not depend on the order in which you differentiate. So I should consider the third order derivatives. And just applying the chain rule, I have the following expression in the first line. Then on the right hand side, I have now the derivative of f with respect to d1 d gamma d nu. But what is really important is that applying the chain rule, I had to differentiate my function f capital. That means I have now third order derivatives. And because I get this substitution v gamma being equal to eta gamma delta d1 by d delta f, I also have it multiplied by eta mu nu. So now I may apply my flows to d1 d gamma d nu f. So I express d sigma d nu f and differentiate it with respect to d1. Again, applying the same procedure, well, as we did for the first equality, I get the following expression. And the property of commutativity of the flows is now equivalent to the fact that what I have on the right-hand side of this equality is symmetric in sigma, alpha, and beta. Well, being symmetric in alpha and beta is very simple because I have this alpha and beta only in the third order derivatives of f. But being symmetric also in sigma, well, is some special property. And this special property holds exactly because WDVV equation holds. Because WDVV equation indeed says that if I take this expression inside brackets, then I can interchange alpha, beta, sigma, and even mu tilde, I think. Oh no, nu. Not nu tilde. Yeah, nu tilde. So, namely, in this way, we get exactly that the commutativity of the flows is nothing special, but just the statement that the product of the Dubrovin-Frobenius manifolds is commutative. Oh yeah, and a very important thing is that indeed, in order to employ this fact, you have to use this very important stabilization property, that whatever your indices alpha, beta, and sigma are, you can take some minimal n, that should be a dimension of your Dubrovin-Frobenius manifold, for which you can write down all these formulas. Yeah. So, how is this all generalized? So, the point is that if WDV equations came from cohomological field series, well, all the theory of the Dubrovin-Frobenius manifolds was introduced to study WDV equations. There is an open version of Grom-Witten series and, well, probably open version of cohomological field series. That is not really well settled up to now, but at least in genus 0, it is proved that the intersection theory of open, well, of any open coh of T should satisfy not just a usual WDV equation, but open WDV equation. It says that it should provide not just one function f, but two functions f, where the first function, I will just call it f, is a solution, or f or fc, sorry, fc, saying closed, or well, that is opposing to open, that fc should be a solution to WDV equation as we had previously, and fo is some new function. It depends on one additional new variable v0, and once again, one can define a product. This product is now defined a little bit differently, namely this VO provides the, well, dependence on a new vector d by dv0. And once again, this product should be associative. Well, this is equivalent to open WDV equation. So the potentials of this, well, first of all, yeah, I should say about the examples. The examples of such solutions to open WDV equations, well, they exist. And in particular, they are given by the so-called open R-spin curves, corresponding to functions fc being the Dubrovin-Frobenius manifold of A type. And well, one can prove the following interesting thing. So we know that FAN, the potentials of the Dubrovin-Frobenius manifolds, they satisfy some stabilization conditions. So we have found it previously. And the point is that also the open potentials also satisfy the same stabilization condition. This is a, well, new interesting thing. So namely, now one can define a new set of constants. I write it here Rax, and this set of constants extracts the data from the open potential, not just FAN, but the open potential. And well, again, you can write down the system of PDEs. The first line in this system of PDEs is exactly the old line. So this is just the specialness KP hierarchy as it was. And now you have an additional line. Recall also that still, if you set the new variable v0 in here, yeah, of fo brings a new variable v0. So if you project everything to v0 being equal to 0, then you get an old Dubrovin-Frobenius submanifold of type A, like it was before. So therefore, also in here, you have two additional flows. one corresponding to the old flows of the Dubrovin-Frobenius, and the new flow D0 D alpha F coming from the open part. So it's important to say that these solutions of open-WDVV equation, they cannot be written as solution to WDVV equation. So you cannot integrate this function fo so that you get one new Dubrovin-Frobenius potential. Well, it's not true. So it basically doesn't work. There are geometrical reasons for that. So you cannot write the same in the context of the Dubrovin-Frobenius manifolds. But still, you can extract these constants from two potential, from the closed potential and open potential. And the miracle is that once again, you get a commuting system of PDEs. In this particular case, one can basically check that what you get here is a system of dispersionless modified KP hierarchy. But actually, once again, you can prove commutativity of these flows just from the associativity of the product. But the product now it's a modified product involving, well, being set by two functions, f and fo. So yeah, and modified KP hierarchy, well, I don't know if I should explain what it is. Once again, it's, well, you take, and you can write it in a phase form too. It looks to be close to what we had previously, but now you have one additional variable T0, well, with some little bit special dependence. So, well, I have like 15 minutes left. Well, I promised to say something about the B-type Dubrovin-Frobenius manifolds. Well, maybe I don't say everything I can, but there is still a big question. So if one takes the integral hierarchies associated to A, D, then actually there is a, well, very well settled construction of Drinfeld and Sokolov who associate an integrable hierarchy not just to a Coxeter group as it was for the Dubrovin-Frobenius manifolds, but to Lie algebra. That means you have a more refined data, not just a Coxeter group, but a root system. And it's not distinguished by the Coxeter groups, but it is distinguished by the root systems. There are root systems of B and C having the same Coxeter group. So there is an essential question: how to construct the integrable hierarchies of Drinfeld and Sokolov from the Dubrovin-Frobenius manifolds. In the case of A and D, the Dubrovin-Zhang hierarchies are the same as Drinfeld-Sokolov hierarchies. Well, it was known for A, but for D, it was only really proved in the work of Liu Zhang. Well, but an open question should be how to get B and C integrable hierarchies from the Dubrovin-Frobenius manifolds. Well, it was answered by Liu Zhang and, well, sorry, Liu Ruan, I think. Yeah, Ruan, definitely. That such hierarchies can be constructed from the Fanjaros-Ruan series, also of A and D, but with the mirror pair potential. But how to construct them from what I do here? And the answer is actually the following. The answer is that if the Dubrovin-Frobenius manifold of B and C is not distinguished, that means that one should write down the dispersionless B hierarchy using the Dubrovin-Frobenius manifold, and this can be done. Actually, for example, even these flows in here that are the D flows, yeah, in D flows, these are the flows of BKP hierarchy, of the honest dispersionless BKP hierarchy. Then the way how to get a full hierarchy is now to H deform these operators D by dt. And well, how to get different and indeed Drimfeld Sokolov BC hierarchies is to consider the different H deformations of these variables, of these differential operators. So, but that's still an open problem. Well, if not going into the full hierarchies of B-type, well, there is another interesting construction that was introduced by Bertel and D.Zuo. It's rather special for B-type. It's not present for A-type. And the point is that it does not have only one construction of a Dubrovin-Frobenius manifold, but for Bn, where n is a rank of a group, of a root system, you get exactly n different constructions of the Dubrovin-Frobenius manifold. These are indexed by k. If you take k being n, it's exactly Dubrovin's construction, and the potential is polynomial. But if k is n minus 2 or smaller, then you get a Laurent polynomial in one variable Vn, and those are, well, in principle, at least different potentials. So there is an essential question: if one can build up, if one have some stabilizing series of potentials, and if there are still some integrable systems beyond that, and the answer is actually positive. But in here, I have to reorder a little bit the variables, so that now, recall, I had this n being the dimension of manifold and one additional number n. So I take now the variables being from k and lower. Namely, it should now have also the negative indices. That's okay. And the point is that all these potentials, they also have some stabilization properties. And these stabilization properties, those are special. And if previously we had these special stabilization properties, for one set of variables and with some additional new variable, like it was for D or open A, here we have three different sets of special stabilization data. The first one is when both alpha and beta are positive. One of them positive, the other negative, and both negative or equal to 0. So this is the stabilization property, and recall, look at here now, it depends not just on n, but on the difference of n. So on the left-hand side, you have the second order derivative of fkn, on the right-hand side of fk plus p n plus p. So, and the statement about that is that if you consider, once again, as we had previously, the system of PDEs introduced by taking the second order derivatives of f and putting there the clever substitution, well, then you get a consistent system of PDEs. Well, this system of PDEs has now three special flows, three special systems. Once again, I skip here the flows corresponding to alpha and beta positive because they indeed coincide with the dispersionless BKP flows. It's once again nothing special because one can show that for this BKN, the Dubrovin-Frobenius manifolds. So recall here I made this substitution so that I have the variables positive and both negative. So if you set to 0 all the variables that are equal to 0 or negative, you just get the potential of BK, the Dubrovin-Frobenius manifold. That is the same as to take last variable to be equal to 0 in dk plus 1, the Dubrovin-Frobenius manifold. So this is once again a Dubrovin-Frobenius submanifold. So the product is closed, well, under the multiplication. So, and that's the reason why one gets the special flows that are, well, independent on the other variables and initial data of the other types. So, and the other flows, if one takes one of the variables to be T0, then those can even get, well, they always get some fractions. So that's because the potential of the Dubrovin-Frobenius manifold was not just a polynomial but a Laurent polynomial. So for these flows, I actually don't yet know how to associate them with any well-known hierarchy except for the BKP flows, depending on the positive times. Well, but the others are still work in progress. So yeah, thanks for your attention. That's all I wanted to say.
Okay, thank you for your talk. Any questions? Probably from Zoom or from audience.
Let us say. Alexey, any comments about C-type root system and the corresponding Dubrovin-Frobenius manifolds?
Well, about the C-type, well, it's like with B. So B and C Coxeter groups basically coincide, and they give the same Dubrovin-Frobenius manifold. So actually, we have seen this Dubrovin-Frobenius manifold. It was exactly the submanifold of Dn with the last variable being equal to 0. That's exactly that submanifold. So that's also the Dubrovin-Frobenius manifold of type C. So then it's really easy to write down the dispersionless hierarchy, and this will be the same for B and C. This is dispersionless BKP hierarchy. Well, all the interest in B and C hierarchies is now to give them not just dispersionless but full. And for that, one has to do a clever trick. So one has to introduce indeed this clever H deformation. Because even the procedure of Dubrovin and Zhang, well, doesn't work. So they have a clever procedure how to construct a full hierarchy from its dispersionless limit, but in the case of B and C root systems, it doesn't work. So here, well, one has to get a clever H deformation. Well, actually, this is possible. This is just the matter of time. Well, that's something to do. More complicated is how to justify it from the point of view of the Dubrovin-Frobenius manifolds.
Okay, thank you. And probably one more question. This Dubrovin-Frobenius manifolds corresponds to dispersionless hierarchies. And in A-type, you showed us that it is a clever way how to just extend the dispersionless to full, probably with the same coefficients given from Dubrovin-Frobenius structure, but with different differentials. Is it the same for D-type or B-type?
Well, that's exactly the H deformation I was speaking about just now. Well, for the E-type, our theory doesn't work because we need indeed an infinite family. And in E, you don't have an infinite family. So because of that, it basically doesn't work. We can't even construct a dispersionless limit. Well, and indeed, for A, I gave the correct H deformation, and I didn't give it for D. The point is that if one gives it for D, this is the same as to give it for BKP. Well, that's the matter of time. So I'm pretty sure it can be done, but well, I didn't do it yet. So yeah, but for example, for the modified KP, yeah, it can be done. One should consider just the same H deformation for all the variables we had for KP, and there is additional T0 variable. Well, there are formulas how to modify it. Well, they are very similar, but with a sign. So one can get a full modified KP hierarchy from the dispersionless limit by the same formula.
Okay, thank you. Any more comments or questions? If not, let's thank Alexey again.
Thanks.
And stop the recording.